Hey guys, you're watching Python tutorials on my YouTube channel Python for Microscopists. Well, please remember that this is not just for microscopists, this is for anyone who is interested in image analysis, especially using machine learning and deep learning. I'm a bit excited about this video today because I'm hoping this summarizes artificial neural networks. In case you have any questions about what it is, this video should be the mother of all of these videos where I'm hoping this gives you the aha moment. Oh, now I understand artificial neural networks. That's the intention of this video. So for that, I'm going to use a very simple data set that we all can relate to and easy to understand. I'm going to first analyze that data set, in fact, fit that data set using linear regression that we all pretty much feel very comfortable about, and then use a very simple neural network to predict, using the data from this data set. But as we go along, I will explain the weights, the biases. We'll have a look at it. We'll have a look at the activation function, how it is actually fitting into this entire scheme. And we'll not hand calculate, but almost look at the weights and biases and calculate the output. So this will walk you through the process. And again, like I said earlier, I hope it leads you to this aha moment. Okay, this is where you can get a bit more interested into neural networks, and I hope I'll do I justify the statements I just made. So first of all, a quick reminder, right? I mean, what is linear regression? You have some data that we plot. Again, on the x-axis we have independent variables, right? The time of the day. And on y-axis, we have dependent variable represented usually with the letter y, right? On x-axis, you have x, on y-axis, you have y. And on y-axis, it's dependent, okay? How is the temperature changing based on the time of the day, right? So that's your y. And you can have multiple x's for your problem. Okay, and we'll see that in a minute. So linear regression is all about fitting a straight line to the data by minimizing the mean squared error between the actual data points and your straight line. Okay, please watch my linear regression tutorial if you don't know what I'm talking about. But at least I hope you know that linear regression is just fitting a straight line. Now in real life, you may have multiple x values, meaning multiple factors are contributing towards your result. Okay, in which case we use multiple linear regression. So instead of y equals mx plus c, we have y equals, okay, c or beta 0 in this case, plus this, plus this, plus this. And here, this is our dependent variable, right? The output, the outcome, the prediction. So this is what we're trying to predict by modeling all the input variables. And then comes these x1, x2, x3, and so on. These are independent variables. Time, okay, could be an independent. I mean, it's often the independent variable. There could be many other independent variables, right? So this is these are independent, and this is if you plot it, this value is the intercept for a straight line. Okay. Let's consider this, or let's introduce a new term called bias. Okay, so this is what we call bias. We are adding bias to this equation, and this is slope, right? I mean, beta 1, beta 2, these are all slopes of the straight line when you plot the straight line on your x and y axis. And let's call them weights for now. And I'm introducing this term because, again, later on, we'll use the same terminology for neural networks. So think of this: outcome, our prediction, and x's, as you know, these are all our features, attributes, independent variables. And these are weights, and this is bias. Now let's have a quick look at the neural network and artificial neuron. Again, you probably saw this before, but if you're watching a neural network video for the first time, let me quickly summarize this. This is an artificial neuron in the middle. Okay, this is represented. This is an artificial neuron, meaning multiple inputs are going into this artificial neuron and it's giving an output. What happens in there, we'll talk about it later, but multiple inputs are going in. Okay, and in addition to these multiple inputs, the extra input called bias. Okay, remember, we just introduced the term bias right there. Think of that as also being an input to this artificial neuron. And these are all calculated. Okay, these inputs that goes in as part of these iterations in our neural network, the bias is updated every time a new iteration goes by, and the what we call the weights, you see, W1, W2, W3, W4, all of these are weights, and these x's are the x values. So think of these x's as these x values, and this beta 1, beta 2 as the weights here, yeah, W1, W2, and this bias is the bias. So I'm not saying linear regression and deep learning are the same, but you can see the similarities here, right? So you have very similar structure right there. And based on that, it's literally nothing but a summation function, okay? This is exactly like here. When you add all of this, that's of course what we call summation, right? So this whole thing is an artificial neuron, and when the output actually comes out, we add something called activation function and then gives the neuron output. So think of this entire thing as an artificial neuron that's composed of a bunch of inputs multiplied by weights, added a bit of a bias, and it goes through activation function, and then you get neuron output. Activation function can be as simple as, okay, it's a straight line, input versus output, or if the value is below something, it's 0. If the value is above something, it's 1. Activation functions, again, we'll get to that again in a minute when we see the actual code. So with this information, let's actually jump one level deep now, okay? So when you define your neural network in Keras, for example, well, in Python, but in Keras, this is how you define. Use the sequential method. And I'm saying, okay, my model equals to sequential. Now I'm adding layers to my model. So the first layer is a dense layer. The second layer is another dense layer, which is the output layer in this case. And I want to compile this model using mean squared error. That's because in this model, I'm trying to predict an actual number. So this is a regression problem, not a classification problem. Classification is this a cat or a dog or a monkey? Regression is the value 1.2, 20.6, 5.372, whatever that output we are predicting, right? So that's a regression problem. So that's why we're using mean squared error as the loss function. Again, let me just go back, which is exactly same as this, mean squared error. Very similar to the linear regression here, right? Typically for regression problems, you try to use mean squared error, okay? Which is, again, if you don't know what that is, you have the actual data point here, you have the predicted data point right there, right? So the distance between these two is your error, right? The difference between these two is the error. But only one data point is not enough, so you have to look at the error of data point 1, data point 2, data point 3, and then square it because the data point may lie below the line or above the line. So you square it to make sure you don't cancel these numbers out, and then you add it and then average it to get a mean squared error. That's exactly what we are using here. Mean squared error as the loss function. And the optimizer we are using called Adam in this case, the optimizer can be, you probably hear the term stochastic gradient descent and so on. Optimizer is basically the algorithm that updates the weights based on the mean squared error. So let me put it this way. Optimizer is trying to minimize the mean squared error, and if the mean squared error is the minimal, then that's where your final result is going to be, okay? Okay, so this part I hope you know, but this would be a good reinforcement of the knowledge. Now, when you print this summary, the output looks somewhat like this, okay? So this is a very simple neural network, and we're going to use this. And this is more than enough for simple problems like the ones we're going to see. So the first layer is, again, a dense layer. I'm not going to explain the difference between convolutional and all that stuff because I've done it in a different video. This is just, again, a quick summary of artificial neural networks and how the biases, weights, and activation function, everything come in together in creating, this model. So the first layer is dense, and the output shape is two neurons are, you're getting two outputs, and the next final layer is giving you one output because we are predicting only one value, right? We are actually predicting a regression value. Again, if this is a multi-class classification where you have cat, dog, monkey, other stuff, then the output would have 5 right here. Now this, I don't know if this part is clear for you guys, like how many parameters are there in that layer that need to be calculated. You see, trainable parameters are 9 in the first layer, 6, in the second layer 3, total 9 trainable parameters. In real neural networks, you have hundreds of thousands, and sometimes you may have million parameters to train. That's why it takes days and days and days. Now, what the heck does that mean? Now let's go one more level deep in understanding what this is. Okay, so for that, let's actually use this visual because it's easy for us to think this way. So initially, you have your inputs going in, right? Think of this as input layer, okay? So this is where the layer is. This is where the second layer is. This is where the final layer is. Normally, you may have multiple hidden layers, right? So you have hidden layer 1, hidden layer 2. Hidden layer is basically anything that's hidden inside, in between input and output layers, okay? So my input layer, for this tutorial purpose, I'm going to call it layer 0. And then this one, I'm going to call it layer 1. Although this is typically referred to as hidden layer, and this one is my layer 2, okay? Now, these are my inputs. For example, this input can be what is our X, right? Time. Time is input in our example. And what is our output? Temperature is the output, okay? So in this example, let's say here we have 2 inputs, time and something else, okay? 2 inputs. And the hidden layer has this neurons. Again, these are all different neurons, right? So this is a neuron, this is a neuron. The neuron is making a decision and giving an output. And this output and this output are going into the final neuron. And by the way, here you can have, again, multiple layers and you can connect them. That's why these are called dense layers, because every neuron is connected to every other neuron. You see, from here, you have a connection to this, you have a connection to this. If you have 10 neurons in the hidden layer, you'll have 10 connections from each neuron, and then for this neuron 10 more connections, and so on. So then your parameters, trainable parameters, would go up. Okay, so from every one neuron, every other neuron is connected here. Okay, so this is a fully connected dense layer. Well, dense with only 2 neurons. Okay, now what do we do? So first of all, from this neuron to these 2, there are weights associated with this. Think of this as, again, the parameters in the linear equation we are multiplying the input variable with, right? Variable 0, variable 1, variable 2, and all that. So in this example, we have weights. And there are 2 weights because there are 2 neurons in the hidden layer, okay? Weight corresponding to input data 0, 0, and 0, 1. And these 2 are also different weights, right? So for the next input, we have 2 different neurons. In fact, the example that we're going to work with is a heart disease example, where you can predict whether someone is vulnerable to heart disease based on whether they do regular bicycling and whether they're smokers. So we have 2 inputs. So on X, the amount of bicycling that they do or exercise that they do, and X1 is the number of cigarettes that they smoke, and the output is the risk of heart disease. Okay, now I hope things become a bit clear. Okay, when it comes to bicycling, what are the weights of bicycling, okay, for this hidden neuron and this hidden neuron, and what are the weights of smoking for this hidden neuron and this hidden neuron? So there are 1, 2, 3, 4 parameters that need to be calculated, plus each neuron, if you remember from the diagram in the previous page, has biases associated with it. So there are 4 plus 2, 6. So if I go back, here, this 6 corresponds to these 6. Okay, the 4 weights and 2 biases that it needs to calculate there. So it's, again, if you go this in a methodical way, you will find that, okay, everything makes logical sense. So here you have these 6. Now what happens? Now this is a summation, right? It calculates at this point. So what is it calculating? Well, your input value, x0, multiplied by this weight, plus this value, multiply that weight, plus the bias, right? So this multiplied by that, plus this multiplied by this, plus bias. Exactly same for this one, okay? This input value multiplied by the weight, plus this input value multiplied by this weight, plus the bias, okay? Where are these weights coming from? That's a good question if you're asking that. Initially, at the first iteration in the neural network, or they call it epoch, okay? In the first epoch, the weights are randomly initiated. We don't know what the correct weights are. And then it goes through one loop and comes back And this is where the gradient descent is amazing, okay? Or the Adam function, for example. Adam is like gradient descent, okay? Again, what am I talking about? Right there, optimizer, Adam. This is the one that's actually using and looking at mean squared error, and it calculates this mean squared error, and it's like, okay, now let me update the weights based on minimizing this mean squared error, and then it does epoch 1, epoch 2, epoch 3, and if it's going in the right direction of minimizing the error, it keeps going. But if the mean squared error increases, it goes, and then that's the wrong direction. Let me go back in the other direction, and then it finds the minimum. Okay, so that's how things actually work. So here you have this calculation. Now the weights, let's say, are updated and then updated and then updated. So these values are updated. Now that means what comes out of this is this value and the activation function. So the activation function either activates it or doesn't activate it, right? So if this value, for example, is 0, let's say if this value is negative something, which means it's less than 0, okay, then the activation function will output a value of 0. If this value is positive, then it just reports the positive. So ReLU activation function is nothing but the maximum between 0 and this value. That's pretty much it. You see below 0, it's actually the value is 0, and below above 0 for this parameter for a value of x, it is equal to x. So that's all activation function is. This is ReLU, but there are many other types of activation functions, so sigmoid activation functions and other activation functions. So depending on the application, you can pick the right activation function. But ReLU is very common for these type of applications. Anyway, which basically means if I get a very high number right here compared to 0, then that value goes to my output layer. If I get a high value down here, that value goes to my output layer. So what happens at the output layer? Well, exactly the same type of math. Now you have weights associated here, weights here, bias there, and then the same type of math happens, and then the activation function again, because this is also a neuron, and then you get the final output. I hope this makes sense. Okay, again, very simple to follow. You have your inputs, you have your weights and biases, and again at this neuron you have 3 parameters, right? This weight, these weights, and the bias that need to be calculated. So if I can go through all my animation to this slide, you see this 3 right there. This 3 corresponds to the 2 weights and 1 bias that it has to calculate. So when you look at the total parameters, it's 9. But if you have convolutional layers and a whole bunch of other layers, then you'll start to see that, okay, total trainable parameters are, I don't know, 500,000, and total untrainable parameters are something else, because for certain layers, there are nothing to calculate. They're just, like max pooling layer or something. Okay, so I think we are all set to jump into the code to finish or to fill any other gaps that are left in your knowledge, in your understanding of the application here, so of neural networks. Okay, so for that, I'll include this list so you can download the data, but the data that I'm going to look at is the heart disease data, like I just mentioned, which is basically 3 columns. So the first column is called unnamed. This is basically just numbers 1 through how many of our data points we have, so we can drop that. That's irrelevant. The next column is called biking, and the next one is smoking, and the last one is heart disease. So the amount of biking, the amount of smoking, the amount of heart disease. So let's quickly plot these to have a quick look at how it looks like, and then let's get into the actual deal. Okay, so let's drop the unnamed 0 column like I just mentioned, and let's go ahead and plot first of all the biking and then smoking, and then let's quickly have a look at it under here. So this is the biking. In fact, let's clear all images. Sorry about that. I was testing something else. Okay, and then this. So now you can see this is the biking. If you do more biking, if you're very active, then you have less risk of heart disease. So please go ahead and exercise regularly. Now, smoking, if you smoke obviously a lot, then you have higher risk, but it's not highly correlated, but still higher risk of heart disease. So this is, we know that if we fit this to a straight line, what do we get? Y, which is my heart disease, equal to, because the slope is negative, negative biking times whatever the slope is, plus this bias, right? Or the intercept. Same thing if I do smoking, the slope is positive plus this intercept. Now, if you do multiple regression, meaning when you combine these, then what you get is, again, I'm not going to go through all of this. All I'm trying to do is get the data ready for my linear model and then linear regression. Please watch my tutorial about linear regression, and I hope you know what I'm talking about here. Just taking my data and dividing that into training and testing data sets, so I can just use the testing data set that has never been used for training to test the model that we just are putting together. Okay, let's go ahead and fit the model. Again, this is linear regression. And let's go ahead and print the score. Keep an eye on the score, okay? The score is 0.98, which is very good. It's 98%, okay? And let's also print the mean squared error by comparing it against the test, okay? Again, this is why we are holding out the test data set. So let's go ahead and do that. And our mean squared error, excellent, 0.0003. That's amazing mean squared error given our values. Okay, now let's do something. Let's actually look at, again, if you remember, let's go ahead and, sorry about this, let's go ahead and open this. You see this equation? Now let's go ahead and print out this beta 0, beta 1, beta 2 values for linear regression. How do we do that? Well, you can easily do that by using model.coefficient and model.intercept. So let's do these three so you can actually see coefficient 1, coefficient 2, and intercept. And coefficient 1 is negative 0.2, okay? Which is, we know that because for smoking the slope is negative, and for the sorry, not smoking, for biking the slope is negative, and for smoking the slope is positive, right? And then the intercept, which is, we called it intercept, is 15 point something something, okay, right there, 0, 1, 1. Now let's take the two values. I think if you look at our df right there, the first value is 30.8012. Let's just take 30.8, and then the y, which is, x2 smoking is 10.9. So let's take these two and predict the outcome and see if it's working fine or not. So all I'm doing is this multiplied by coefficient 1 and this multiplied by coefficient 2 plus intercept, right? So this should be pretty straightforward. And let's look at the output. It's coming up to be 10.8. Now, what is our output supposed to be? 11.7. That's not bad. And please go ahead and test with other values. Now let's actually see how neural networks, I think this is what you tuned into this video to begin with. But I hope linear regression is clear enough. Now let's get to the next part. So for that, let's clear everything we have here. Okay, and start with a clean slate. I'm cleaning out all my variables. Exactly the same data set I'm going to use for this example. I'm dropping the unnamed, and I'm plotting pretty much the same plots. I just copied the data all the way up to here. I copied the code all the way up to here. Okay, but down here, I'm actually defining my own network. Again, this is exactly the same code. So the network here is, we are using sequential method. Again, this is part of TensorFlow.keras.models. And then I'm adding a dense layer with my input dimensions equals to 2, right? We have 2 columns. So input dimensions is 2. So 2 neurons are going in again, just to show you where we are. Where are we? Here. So we have 2 inputs. One is biking, one is smoking. So that's my 2 inputs here. And the output has only one output. So that's what this is, and I'm using mean squared error as my loss function and optimizer Adam. Again, I made individual videos on each of this topic. Please watch those. So we have our model. Now let's go ahead and fit the model first with 50 epochs. Again, epochs is let me put everything here so it's easy for you to see. Epochs is number of times it's going through this entire data, and 50 for now. Let's do it. I'll increase that to 500 or 1,000, but let's see what happens. So let's fit this. It should be pretty quick. We don't have much data anyway. Okay, it's done. Okay. Now let's actually do our mean squared error just like we have done the last time. The mean squared error here is 2.17. Not good, because with our linear regression we got 0.00 something. So not good because it's only 50 epochs right now. But what I wanted to show you is when we plot the loss function for validation and training, you can see that, okay, my training loss, this is classic, deep learning validation and training losses. And sometimes you'll see the validation loss to be lower and training loss here and so on. In fact, I plan on making another video in terms of what type of different graphs that you will see when you plot loss and the number of epochs, and what to interpret. Yeah, if the red line is above this, or if they cross, or if they are like completely off, how to interpret. And I'm trying to find the right type of data to justify my video. Please stay tuned for that specific video. But until then, we know that here these two need to converge. So let's go ahead and increase the number of epochs to 500. Let's make it 1,000. Why not? So we can see maybe 500 is enough, but let's do this, and I'll pause the video. This may take not much, but few seconds. Okay, so that took about 45 to 50 seconds, and I'm not even using GPU. This is just CPU on a very old computer. In fact, almost 6 years old system. So hopefully you should be able to repeat what I'm doing with your system, or you can do this in Google Colab if you want. Okay, now let's predict our mean squared error. Hopefully this should be much better than 0.2. This is now 0.00024. I think this is very similar to what we have gotten, if not better, than what we have gotten using our linear regression. Okay, obviously we are using deep neural network for a very simple problem. So this is I only think of this Indian saying where you use Brahmastra on a bird, which is like using a nuclear bomb to kill a bird. Anyway, but anyway, our point is to understand the weights, which we'll get to in a minute. Now, let's go ahead and plot it. You see how these things didn't converge until maybe 500 epochs would have been okay, but 1,000, nothing wrong. We didn't see, and these are very nicely converging. So I'm very confident about the model, and let's go ahead and print the weights. I'll share the code so you can repeat this, but the weights can be weights for each layer. Each neuron can be easily obtained by using model.layers. So all I'm doing is going through each layer and printing out the layer depth, and for each layer I'm getting the weights, okay, for layer 0 and 1, okay, within that layer, and then I'm just printing the biases and the weights. So in a way that it's easy for us to understand. So on the right hand side, keep an eye. So my bias to layer 1 neuron 0 is 4.96. Layer 1 neuron 1 is 5.25. So if I open my image again, so these are the values that I'm talking about. Okay, so the bias is right there, and then comes the layer 0 neuron 0. This is the weight, and this is the weight. So these are the weights right there. Okay, this, and then the weights here and here. So and then comes layer 1, so layer 0 and layer 1, right? So layer 1 is right here, and from here you get these weights and the biases. Okay, so those are the ones that I'm reporting here. Well, I've done this once before, and let's see what values. I think I didn't get values that are much different than my earlier run. So here I have 4.4, 4.5. Each time you get different results because obviously the initial weights are randomly added, randomized, and then you converge to slightly different position every time. So, but overall, these are the values I'd like to use. And now what do we do? Okay. Let's say my initial values are 30.8 and 10.9. Remember, these are exactly the same values that we used. If we can open my X, 30.8 and 10.9, right? So to predict our Y. You can take any of these, it doesn't matter. Hopefully this model should work for any number, right? Because we are fitting it for the entire data. Okay, so these are my input values. So these are my x0 and x1. Now let's calculate this, which is multiply x0 with the weight plus x1 with the weight plus bias. So that's exactly what we are doing here. So x0 multiplied by that, well, I'm truncating it, so the values are a bit different. x1 times this multiplied by this plus the bias right there. I do the same for my hidden one, which is this one. Okay, I do exactly the same for that. And here, look at this, max between 0 and that. The reason I'm doing that, max between 0 and that, is because our activation function is max 0 or that. That's exactly. So in summary, I'm calculating the output value right there. And then what am I doing? And then I take this hidden 0 and hidden 1 as inputs to the next layer and multiply by the weights and the bias, and then finally look at the output. This is our final output, right? So that's exactly what we're looking at. Okay, so let's go ahead and run these, and hopefully we should get something that makes sense. It says 10.45, and what is our y for that? 11.76. That's not that off. In fact, let's do the second point, which seems to be very different. 65.1292. Let's go ahead and input 65.1292, right? 12 and 2.219. Let's go ahead and put everything there, and let's not change anything and run this, and let's see what the output looks like. 3.19, and what do we have for output there? 2.85, very close to 3.19. So generally you can see the trend, and you can get you know, the accuracy from our R-squared value, which was pretty good anyway. Okay, so I hope this kind of clarifies any questions that you may have about artificial neural networks. In fact, I hope that you found these, I don't know, 30 to 35 minutes to be very useful for you. And in the next tutorial, in fact, let me prepare for explaining these type of loss functions and what insights can we gain just by looking at the loss functions. How can we improve if we can do anything? Yeah, so let me work on that. Until then, please go ahead and practice this, and I hope you feel enlightened now. Please subscribe to my channel, and thank you very much.